Yeah, so I'm Nate. I'm going to talk about patient contrastive learning, which came out of a collaboration between the Computational Cardiovascular Research Group at MIT and the Machine Learning for Health team, which is part of the data sciences platform at the Broad. So just a little background, and I guess we already have seen some of this the previous talk, but contrastive learning is a type of pre-training, and pre-training is a way to get better performance with less labeled data. So the idea is pretty simple. You train a neural network on a large data set. In this example, something like ImageNet, just a bunch of images scraped from the internet, and train the neural network to predict which class those images fall into. So in this example, the parrot gets classified as a parrot. The car hopefully gets classified as a car. And then we copy over part of the neural network and then either fine tune it or maybe train a small model on top of it without changing the original weights. For our new task, which has rarer, potentially more expensively labeled data. So in this example, the contrived task I've come up with is art style classification. So pre-training, in summary, just a way to get better performance on small data sets leveraging larger data sets. And it turns out pre-training is incredibly popular. There's this one website called Hugging Face for language models, and one of their pre-trained language models you can download had over 42 million downloads in a recent month. And similarly, yeah, there are other websites like ModelZoo, one of their most popular models, OpenPose, which takes single images and annotates where humans are and what their pose is, has 15,000 stars on GitHub. But we picked contrastive learning out of all the possible pre-training techniques. So I want to explain why we made that choice. The first reason is just that on medical data sets, supervised pre-training is generally not an option. So that's because labels of medical observationally recorded data are often either uninformative. That's this first case A. This is an ECG, as it might commonly appear in a medical data set, and they're often automatically labeled with something like heart rate. And heart rate on its own doesn't tell you very much about health. It's a single floating point for a long, high density time series. The other option for medical data is something that's very rich, but potentially rare or expensive and difficult to acquire. And that's this case B, where a cardiologist has segmented the ECG into different rhythm classes, which are different ways of the heart beating, some of them healthy, some of them unhealthy. And as you can imagine, that would be an incredibly rich signal to train a neural network on. But since it takes cardiologist labor, it's going to be rare. So supervised pre-training is not an option. However, there are incredibly rich relationships within medical data sets that we might be able to leverage. One example that is salient to this talk is which data come from which patient. And contrastive learning out of all pre-training techniques is well designed to exploit these relationships and connections between the data. And I think overall, just again, motivating why pre-training, we can improve models on medical data on those data sets with smaller rare labels, which hopefully leads to biological discovery and downstream better patient care. So just going to go through a bunch of different approaches people have taken to contrastive learning on ECGs. And I'm going to come back to both the definition of contrastive learning and the definition of ECG. So don't worry if you don't know much about those yet. In June 2020, Cheng et al. did contrastive learning pairing different time segments of long ECGs. These were 30-minute ECGs, and they're really careful about decomposing the bias caused by specific ECG machines. And they trained on 48 ECGs. Kiese et al., which was talked about last week as one of the baseline models, did contrastive learning pairing, again, different time segments within ECGs, but also had the really clever idea to view different leads of the ECG, which again, I'll define later, and call different leads of the same ECG different views of the same thing. And they trained on 65,000 about ECGs. And then Mahari et al., they compared a bunch of different augmentations, both from the time series literature and from more physiological ECG-based literature. And then our work did contrastive learning pairing different ECGs from the same patient with no augmentations. And we had the great privilege of working with 3.2 million ECGs for training our model. And our work was joint work with Aaron Aguirre, Stephen Song, Colin Stoltz, Eric Reinerston, Puneet Batra, my boss, and me. And then the presentation you saw last week, they focused really closely on physiological driven augmentations taken from expert knowledge about the electrocardiogram. And they got excellent results on an open ECG data set using, in some of their experiments, only 1% of the total number of labels. So that's the timeline of ECGs. And I mentioned we used 3.2 million unlabeled ECGs for training our model. And the reason we have those ECGs is work from Brendan Westover at MGB, who hired Eric Reinerston to digitize these ECGs. It's been a huge resource for training our models. And then also Dr. Lubitz at MGH and Puneet Batra and Palladio Kile on the ML4H side. So the data set we trained on had 364,000 patients with a total of 2.9 million ECGs, and then a validation set of, I think, around 10% of the size. And that left an average number of ECGs per patient of 8. With a fairly even sex balance and a wide range of ages. So that's the training data set. And so we had 3.2 million of them, so I should probably explain what they are. The ECG measures the electrical activity of the heart, for those who are not familiar. So an electrocardiogram can be used for indication or early diagnosis for a ton of different diseases. As you can imagine, how your heart beats and how the electrical signals travel across it has really important implications for health. And one other detail that's important is that they have different leads, which measure how the electrical activity changes in the heart from different directions. It kind of gives you a 3D picture of the electrical activity of the heart. And here's an example of one ECG that shows atrial fibrillation, which is just one of the many diseases that could be diagnosed using an ECG. And this one in particular, atrial fibrillation, increases your stroke risk by 4 times if untreated. So again, yeah, just coming back to PCLR now, patient contrastive learning, our work. So PCLR is based on a contrastive learning approach called SimClear. And just all types of contrastive learning, the idea is to train a model basically to decide if 2 things are the same, which is known as a positive pair in the contrastive learning lingo, or different, which is called a negative pair. So in this cute example, we have a cat image. We're trying to learn representations of images of pets. And you apply two different data augmentations to the cat to create a positive pair. So one augmentation turns the cat black and white. The other one turns it cyan and zooms in a little bit. And the neural network has to make representations of those two kitties to be similar. And then on the other hand, when you have a negative pair, that will just be two images that are augmented versions from different original images. So the representation of the kitty has to be different from the representation of a dog. Patient contrastive learning of representations, PCLR, our work, instead of using augmentations, uses the relationship of which data comes from which patient to define positive and negative pairs. So our definition of sameness or positive pairs is when ECGs come from the same patient. Our definition of different is when ECGs come from different patients. And the contrastive loss function requires no augmentations, and therefore a lot less domain-specific knowledge. So it can be potentially applied to any modality, any medical modality where there are multiple ascertainments per patient. Think of all the different types of medical scans like chest x-rays that are taken multiple times over a person's lifetime. Let me go back and explain this diagram. So on this left-hand column, we have two ECGs from the same patient, and let's just follow one of them going through the neural network. First, it goes through an ECG encoder, which we used a 1D convolutional ResNet, and then that outputs the representations, which we're going to use for downstream tasks later in logistic or linear regressions. Then it goes through a nonlinear projection head, which is just a two-layer fully connected neural network, and then that outputs a contrastive projection. And the contrastive projections for ECGs that come from the same patient are guided to be similar. And then contrastive projections of ECGs from different patients are guided to be dissimilar using the contrastive loss. And I'll go into a little more detail into that. So the pre-training objective or training objective for patient contrastive learning can kind of be thought of as picking out pairs of ECGs. So given a reference ECG, one ECG from a patient, we have to select the other ECG from the same patient out of a bunch of other distractor ECGs from other patients. And keep in mind, these two ECGs, the blue and the green one from the same patient, could have been acquired 15 years apart in our training data set. And depending on our batch size, in this case, 512, the chance accuracy would be 1 out of 512 for random guessing. Now, if you've seen Spirited Away, this is maybe a bit of a loose connection, but I just love the movie. It's kind of like the scene at the end of the movie where the main character's parents have been turned into pigs. And those are a bunch of ECGs from other patients. And she's one of the ECGs. And then the kind of evil, kind of good witch lady is the contrastive loss function. And so our main character has to pick out the ECG from all the other distractions. Oh yeah, sorry, that's a bit of a reveal. But I guess the question is, would the movie end well if we used our model? It turns out that
I gotta start. This is the best. This should get the prize for the best analogy ever.
Thank you. So yeah, the movie would end well 94% of the time, which is pretty good odds. So out of 512, there's a 94% chance of the model finding the correct pairing ECG. And here I have a plot of the accuracy based on how far apart the two ECGs are. So at this 10-year mark, for example, this blue dot says that if the ECGs are 10 years apart, then the model has about an 80% chance or so of guessing that the ECGs of pairing the correct ECGs out of all the distraction ECGs. And you can see that the accuracy does fall off as the ECGs get farther apart. And that's just because it's a much harder task as the ECGs get farther apart. Your heart is different when you're 35 versus when you're 55. But again, chance accuracy is almost zero. So even 50% accuracy is respectable. And we can look at like a particularly interesting case. Here's the patient with the most ECGs. They got hundreds of ECGs in this 30-year window. So in this plot, we're going to start at the patient's first ECG and then go throughout time as they get more and more ECGs. And then the y-axis is the cosine similarity of that contrastive projection of the first ECG with their ECG at the time on the x-axis. So this first point up here at 0 years is the cosine similarity with the first ECG and the first ECG representation. So that should be 1. And then as we go on average, the cosine similarity with the first ECG and the current ECG goes lower and lower, but still is much above the average cosine similarity to like other ECGs. And I've marked in the green one of the most similar ECGs taken a bit of time after the first one, and this ECG that was actually less similar than 0 according to the model. And we can take a look at what those ECGs look like to get an intuition for the models, how the model's making decisions. So we have their first ECG of many, and then this is that green line about 7 years later, a highly similar ECG according to the model. And there are some differences in relative amplitudes, but overall they visually just look incredibly similar. And then that most different ECG, which was less similar than 0 according to the model, for one thing has a heart rate that's almost double, and also is an incredibly noisy ECG. So this is obviously super anecdotal, cherry-picked evidence, but I think it kind of shows what the model might be looking at. And so we've seen the training results, 94% accuracy at pairing ECGs. How effective are the representations of the ECGs for downstream tasks? This is what we actually eventually care about. So we're going to compare using a ridge regression on the patient contrastive learned representations to classify 4 different tasks to training a neural network from scratch on different sizes of labeled data sets. So first, we're going to look at atrial fibrillation classification. And on the x-axis, we have a number of training labels labeled with yes, atrial fibrillation, or no, atrial fibrillation. And atrial fibrillation is relatively rare. So there are only going to be a few cases out of the 640 training labels. So training a neural network from scratch on 640 ECGs with not that many positive cases is incredibly hard. So you get a bad F1 score. However, training a logistic regression model on top of the Pickler representations of the ECGs actually does pretty well. And then, as you can imagine, as we get more and more labeled training data, training a neural network from random initialization starts to work. But even up to 20,000 labeled data, Pickler is competitive. And again, we're not fine-tuning Pickler. So it's not comparing a fine-tuned neural network to a random initialization. It's comparing to, you get to do logistic regression versus you have to design a whole neural network architecture. And then we can see similar trends, although with different crossover points for the different tasks we looked at. LVH is left ventricular hypertrophy, which is a structure of part of the heart. And again, a crossover point this time at around 5,000 labeled data. And then for sex classification and age regression, we actually didn't even get to the crossover point yet. And these two, sex classification in particular, we'll actually see later in the talk, is something that Pickler turns out to be well designed for, although that was unintentional. We also compared to 3 different baseline approaches. We took a supervised pre-training approach. And for that, we used some regexes on the automated text produced from the ECGs, which led to 6 different arrhythmia labels for every ECG in the 3.2 million ECG pre-training data set, and just trained the exact same architecture as the contrastive learning architecture, except to classify these 6 arrhythmias. And then we use the layer before the classification layer to get representations of each ECG. This would be akin to using the representations from a model trained to classify ImageNet images. We also trained a convolutional autoencoder, which is sort of trained to compress an ECG. And we trained it to really high reconstruction accuracy. But the representation, and then we took the representation at the bottleneck layer of the autoencoder, the kind of compressed version of the ECG, and trained logistic regressions on that to try to compete with Pickler. And then we also trained a version of one of the contrastive learning approaches that came before us. The one that used positive pairs as different leads from the same ECG and different halves, different non-overlapping time segments of the same ECG. And for 3 out of the 4 tasks, patient contrastive learning pretty significantly outperformed the other ones across number of labeled training data. The one exception was atrial fibrillation classification, where the other contrastive learning approach we compared to did a bit better. And that is, I think, partly because their approach is particularly well suited and designed for arrhythmia detection, because different leads of the same ECG should show the same rhythm classes. Any questions?
Okay. Can you elaborate on the last part? That why the contrastive learning approach actually works better for atrial fibrillation.
Yeah. And we're going to talk pretty soon about more of the theory of like what makes a good contrastive learning objective. But the basic idea is that the different leads of the ECG, which are defined as positive pairs in the contrastive learning of cardiac signals across space paper, the different leads of the ECG should share the same rhythm class, whereas arrhythmias show up kind of sporadically and randomly, so they might not be shared if the ECGs are taken at even a day apart for the patient contrastive learning objective.
Got it. Thank you.
Yeah. So just an overview of patient contrastive learning. It turns out patient identity on its own is actually an incredibly rich label, which can build generally applicable representations of medical data. And Pickler yields good results on small labeled data sets, especially compared to training a neural network from random initialization. And we're exploring this avenue a bit more with Julian Haimovich at MGH, looking at structural heart diseases from ECGs using Pickler. And some of those heart diseases, as you can imagine, are pretty rare. And then finally, Pickler representations can be used straight out of the box for many different disease states. We've started exploring this with Xinwang and Sam Friedman on our team, looking at using Pickler representations in risk models for 4 different diseases, 4 different heart diseases. So maybe again, I'll pause real quick there if there are any questions on like the Pickler setup, because we're about to jump into more of the theory of contrastive learning. Okay. Yeah, feel free to stop me anytime. So we saw that using this patient pairing type of contrastive learning objective led to pretty good results. But why? It's a little surprising, actually. So we're going to look at through some recent theory developments in the deep learning community, contrastive learning through the lens of information theory. So first off, there's this paper, Representation Learning with Contrastive Predictive Coding, which showed that for a given batch size n, optimizing the contrastive loss is optimizing the mutual information between the representations of data in the positive pairs. This term here, this negative L theta, is the negative loss overall of the neural network during training. So I think the most important takeaway here is that the neural network is doing some optimization of the shared information between the positive pairs of data, and that increasing the batch size is really important for the particular loss function we used. And that kind of makes sense because as there are more and more distraction ECGs, it's harder and harder to make the right choice. So if you can make the right choice, it means that there's a lot of shared information between the ECGs. I think another paper that gave a lot of practical ideas from the theory is this one, what makes for good views for contrastive learning. And that was also discussed briefly last week in the other ECG contrastive learning talk. And its take-home message is that what you define as your contrastive learning pairs should only have features in common that are relevant, that are features that are relevant to our downstream task. And I'll give an example of that in a second. But they provided this useful figure in the paper. So on the left-hand side, on the x-axis, we see that the pair choice for contrastive learning they picked, the 2 elements of the pair have basically nothing in common. And then, as you can expect, that's an impossible learning task. So the transfer learning performance is going to be a 0. And then, in this case, they're lucky. They've picked kind of a good gradation of contrastive pairing tasks. As the pairing definition gets more and more lenient, there are more and more features in common. And those features in common happen to be very relevant for the downstream task. So the transfer performance gets better and better until the positive pairing starts having features in common that are distractions for the downstream task. So the transfer performance goes down again until the final extreme on the right hand, where the positive pair elements are just exact copies of each other. And so we can look at like a really simple example. If we were trying to classify information from colored shapes. So imagine that we have a bunch of colored shapes and our goal is color classification. Then if we want to get the best results using contrastive pre-training, ideally we should have pairs of shapes that are the same color. But the other important part of that is the other side, we want those shapes. Since we're doing color, we want the shape information to actually not be shared by pairs, because that would be a distraction for the downstream model. And then if we look at the same data set, except we're doing shape classification, then we want the objects that share the same shape, but ideally different colors, to be paired together. Because then again, color won't be a distraction for the downstream task. Looking at this paper, we decided to do some experiments by slightly modifying the patient contrastive learning objective. So the setup is that we take the patient contrastive learning objective, except we restrict the types of pairs that can end up in the training data for a bunch of our models. So either we can, for example, we could set the maximum distance in time between two ECGs in the training data for our model to be 2 years apart, which is what you see. These blue dots are cross-validation scores of representation from a 2 years apart maximum Pickler trained model. And note that the ECGs could also be 1 year apart in this first model. And then we can increase the number of years apart between the ECGs, the maximum number of years apart on the ECGs, and that's what we see going across the x-axis. And then on the y-axis, we have the accuracy of training a logistic regression model on top of the representations from the max years apart different Picklers. Over time, with more and more maximum number of years between the ECGs, the downstream sex classification gets better and better. And the explanation for that in that framework of kind of picking the right shared information between our positive pairs is that more years apart means that there are fewer features in common between the ECGs besides sex, because ECGs, even 30 years apart, are likely to share sex, features, but they're not likely to share any other features, like features related to age or features related to short-term diseases. So the farther apart the ECGs could be, the better for a downstream sex classification model. We also tried age regression using the exact same experimental setup. And this case looks incredibly similar to the figure from the paper a few slides ago, where there's different amounts of overlapping information between the pairs. And it turned out that this 8 years apart model had the best downstream R² for regressing age from the ECG. And again, more years apart between the ECGs mean there are fewer age features in common, but there are also fewer distraction variables in common. And actually, we can drill down even more onto why that 8-year model in particular was really good. It turns out that how age was labeled for our ECGs was rounded to the nearest year. So actually, ECGs 1 year apart in our data set tend to share all of the potential age information, or all the age features. And then if we look at this plot here, we plotted the maximum number of years between the ECGs on the x-axis, and then the average number of years between the ECGs in the y-axis. So in the 8 years apart maximum, there are a bunch of ECGs that are actually paired closer together in the training data set. It's sort of an exponential distribution of how close together ECGs are. So the average for maximum 8 years is actually only 1 year apart in the pairings in the training data. So actually, in expectation, this 8 years apart maximum model is perfectly situated for classifying or for regressing age within 1 year with 1 year precision. So maybe I'll pause here on the information theory section, if anyone has any questions or thoughts. Okay.
So
Oh yeah, go ahead.
there is this other sort of, I mean, this could just have a topic for like the discussion we're gonna have afterwards, but let me just ask it. There's this other perspective on contrastive learning. It's another theory paper from Matthias Bethke's group. I'm hoping I'm pronouncing his name correctly. But basically, they show an interesting deep connection between contrastive learning and nonlinear ICA, independent component analysis. That basically they show that contrastive learning inverts the data generating process, and sort of the representation, the contrastive representation you find, basically different dimensions correspond to different sort of independent degrees of freedom of the data generating process.
Oh, interesting.
So yeah, so I wonder, you know, whether you're looking at it from a very different perspective, from the perspective of like information theory and mutual information. But I wonder whether you can find a connection between these two perspectives on contrastive learning.
Yeah, that's actually that's a surprising connection, that it's connected to the data generating process. Because I've often thought of one of the advantages of contrastive learning is that you don't have to learn the full data generating process. I'll have to think about that. Yeah,
we can chat more about. Yeah, I mean, I think it's a good topic to explore.
Yeah, it's really interesting to think about. Yeah.
Thank you.
So we've looked at patient contrastive learning, the training process we used, the results, and some of the theory for why it worked out. Now on to some future work and some open questions. So as I mentioned earlier, patient contrastive learning as an objective could be equally applied to any different medical modality. And Paolo Diachile and Kavya on our team are working on applying it to echocardiograms, along with other contrastive learning approaches. But also, you could imagine having an encoder for echocardiograms and potentially ECGs from the same patient. So the embeddings from ECGs and the embeddings from echocardiograms from the same patient could be pushed together. And then why not throw in some more modalities? We could throw in the text report that comes in with the echocardiogram, and we can kind of try to unify representations from a bunch of different data modalities. And there's some really interesting questions here about if the different modalities have different frequencies, how can we use a really common modality to bootstrap a good representation from a less common one? And based on the mutual information understanding, we're actually only going to get the information that's in common between the modalities. So we might lose some of the modality specific information. So there's some really interesting questions around how to keep both the intersection information and the union of the information of different modalities to build the best possible representation. And then this is some work with Jackson Killian, who interned with us at the summer and is a Harvard PhD candidate. Can we potentially automatically design the contrastive learning task? Do we need that intuition that we had that patient identity would be a good contrastive learning task? Or can we see a huge data set with a downstream task in mind and build the contrastive learning task automatically? So this involves exploring the scaling laws as we increase the amount of unlabeled versus labeled data? How do the results change? Can we get the most favorable possible scaling law for the labeled data? Because that's the expensive part. Yeah, lots of really interesting questions here on like label efficiency. And what, if you had perfect information, what contrastive learning task would you pick? So that's another direction for exploration. And I guess with that, I'll say thank you to all the great people on the Machine Learning for Health team and the other people we work with at MGH and the Broad Institute.